Great. Okay. Since it's a couple of minutes past 2, I'll just get started. Just before we begin, so Marinho is going to talk to you about dynamics and brain networks. Just before we begin, though, I want to say one of the things that we as a whole were aiming for when organising this workshop was to aid with sort of facilitating collaborations. So now, especially while Kubrick's locked down, while it's going to be a little while before many of us get back in the labs and so on, is a great time to do some more quantitative studies, some modelling and so on. So if you have any ideas, any thoughts, or you're looking to brainstorm some ideas, please get in contact with any of us, myself or Marinho, Alex, Dominic, Zhajang, so on. We're all happy to discuss ideas about modelling and potentially collaborate on some of this stuff. And in particular, we have discussed perhaps running a session to brainstorm some ideas, so you can bring along some ideas with some data you have, or ideas where you think modelling might be interesting. So if you are interested in doing this session, I might, when I send out a feedback form, include a question, see if people would be interested in having a session like this, because I think it would be quite interesting. So yeah, by all means, please contact us if you've got any thoughts at all, or even just vague ideas that you'd like to do some modelling, and we can discuss collaborations and thoughts on this idea. So anyway, Marinho is now going to introduce some dynamics on networks. So last week I introduced some areas of dynamical systems and how we can use these to model a neural mass. And so now Marinho is going to extend this and say, if we treat each region of the brain as a neural mass, how can we model brain networks and the dynamics of connectivity, wire up these different brain regions? And this is going to be really interesting for synchrony, functional connectivity, anything where you have communication between regions of the brain. And in particular, Marinho is going to focus on an application of epilepsy. So if you have any questions, I'm going to be available. I'll be keeping my eye on the chat, and I think Dominic's also around. So by all means, ask in private or in group on the chat, or Marinho, if you're happy for people to ask questions out loud.
Yeah, sure.
Great. So over to you then, Marinho. Thank you.
Okay, thank you. Hello, everyone. So as Luke said, I'm going to focus on the application to epilepsy. So before, in his talk that he gave like last month, he introduced dynamics in very simple models, and now I'm going to extend that to networks, and we will see an application to epilepsy in particular. And this, although I'm going to focus in epilepsy, this doesn't mean that this framework is only applicable to epilepsy. So at the end, I will also show you that actually this is more general and can be applicable to many different things. As Luke said, so you are free to interrupt me at any point to ask me questions. So epilepsy, just to give a brief, very brief overview about epilepsy. For those that don't know, what is epilepsy? So epilepsy is a brain disorder that is characterized by recurrent and unpredictable seizures. And seizures, they are transient occurrence of signs and or symptoms due to abnormal, excessive or synchronous neural activity in the brain. And what does that mean? Well, it means that we can use EEG to find, to diagnose people with epilepsy, for example. So EEG, you probably know that you can record brain activity with this kind of caps, with these electrodes. You can record activity, and so what you find is this kind of activity in each channel. So for each electrode, you have a time series that tells you how the brain activity is close to that electrode. And so this is a typical EEG that you can record from a healthy individual at rest with eyes closed. If there is a seizure, then you can clearly see what happens. So you have here the resting activity, and then suddenly you have this excessive synchronous activity, which is in this case an absent seizure, which is a generalized seizure. It means that it occurs in all over the brain. And so you see it in all electrodes. So some key questions about epilepsy. So what makes a brain susceptible to generate seizures? That's the key question that it's really important to be able to answer in order to develop methods to diagnose people with epilepsy. And also, what are the mechanisms that underlie the transition from the apparent normal brain activity to the seizures? So this is important in order to develop the treatments to stop these transitions to occur. And also to predict the seizures. So if we are not able to stop them, so it would be nice at least to be able to predict if they are going to happen, so that with a certain device, for example, we could alert the person with epilepsy that is going to have a seizure, let's say in the next 5 minutes. And the network neuroscience, it can help us to answer some of these questions, and people have used it to show that actually people with epilepsy have an abnormal brain network. But just knowing that it's abnormal doesn't tell us too much, because even with other brain diseases we can also see abnormalities. But why does a certain change in the brain network, why does it lead to seizures? That's a key question, and in order to answer that we need to go beyond of just studying networks. So we need modeling, and so yes, to move from correlation to causality, we need to understand the why that those abnormalities imply epilepsy. And so we go to modeling, and mathematical modeling, yeah, can help us answer these questions. And then the question is, what models shall we use? As you might remember from Luke's talk, there are microscale or macroscale models. So in macroscale, we are interested in modeling, for example, single neurons. In macroscale, we might be able to model like brain regions. And another question is, are we interested in using biophysical or phenomenological models? So with the biophysical model, we are really trying to model the physics underlying the phenomena. And so we should have a good knowledge about what is going on to analyze a biophysical model. Whereas a phenomenological model, it's usually a much simpler model where we are just interested in some kind of equations that give us the overall qualitative phenomena that we are interested in. And yeah, what kind of model shall we use? It depends what is the question that we want to address on the current knowledge. And I put here the knowledge because, for example, for the biophysical models, they might seem better than the phenomenological, but actually that depends if we are really able to use them with our current knowledge or not. And so possible models in the microscale, just very briefly. So in this paper of Iskevich, you can find, it shows these different models, these 11 models, the single neurons. And so you can see here in this table that, so these are the names of the models, and here the first column tells us if they are biophysically meaningful or not. So minus means that they are just phenomenological, and with the plus means that they are biophysical. And here, if we look at the last column, we have here the number of flops. These actually tell us what is more or less the complexity of the model. So it's how long does it take to compute 1 millisecond of the dynamics in this model. And we see immediately that those that are biophysically meaningful, the biophysical models, which are the Morris-Lekar and Hodgkin-Huxley in this table, both of them have quite a big number of flops. So this means that they are quite complex models to compute. Yeah, in between, we see many different behaviors that we can model with these, with these models that we can see. And so just to give you one example or two, the integrate and fire model, which is the simplest one, as you can see here, just 5 flops. What we have here is that the membrane potential is given by this V. So the derivative of this membrane potential, how it changes in time, is given by I current, a certain parameter A, minus V, multiplied by the membrane potential. So just parameters, I is the input current to the neuron. And if the membrane potential goes above a threshold, then we reset our membrane potential to a rest potential. And that's basically it. So it either is going towards firing a spike or not. It doesn't do much. So it's really simple, but it's useful if we are just interested in studying how the neurons can spike and how they integrate. In comparison, if we look at the Morris-Lekar model, which I show you here, 600 flops. So it's actually these two differential equations with lots of parameters, and then even the parameters are given by these difficult equations. And as you can also see, there are many, many different parameters here. That's why I was saying before that when we are choosing a model, it's really important to know, so what's the question that we, and also what's our current knowledge, because if we don't know all of these parameters, then and if we just choose randomly some parameters, then it's not biophysically meaningful anymore if the parameters are not meaningful. Therefore, yeah, this model might not be appropriate for our purposes. And let's move to the macro scale. The macro scale, we can have neural network models. So this can be meso or macro scale, depends how we want to do. So in a neural network model, basically we can put together many of those single neuron models that we just seen together in a network. So that's what Iskevich and Elman did in this paper that they published a few years ago in PNAS. So they simulated 1 million neurons with 500 million synapses. And so yeah, that's macro scale. Another way is to study neural mass models or networks of neural mass models. And in this case, we, instead of modeling each single, we forget about those details and we take a mean field approach. So that means that we are interested in like population dynamics. We want, for example, to define what is the average firing rate of the population. And we try to define an equation that defines how the populations are firing. And so we've seen already in the previous talk from Luke, the Wilson-Cohen model. There are other models like the Jensen-Reed model, the Wendling model, which is just a version of the Jensen-Reed model. And yeah, there are others. And yeah, for more on this, you can see this paper from Michael Breakspear, which I think that Luke also cited in his talk before. And so in our case, we are going to take a phenomenological model of seizure transitions. Yeah, there are many different models in epilepsy, like the Wendling model that I just mentioned, the Benjamin model, Epileptor. So the Epileptor, maybe some of you have heard of it. It was proposed a few years ago by Victor Chirse, and so it's many people are using it. But here we are going to consider the Theta model, which is a phase oscillator model, which is just given by this simple equation. And let's find out what does it mean. So the Theta model, we have this Theta phase, okay? So we have Theta here, Theta there, and this equation gives us how Theta is changing in time. So Theta is the phase of our oscillator. And to understand the phase, we can remember the unit circle. So as you might remember from maths, if you plot the unit circle, and here you have an angle, Theta, you can project this angle. If you project in the horizontal axis, you get the cosine of Theta. And if you project in the vertical axis, you get sine Theta. And if you check the tangent here, it's the tangent of the angle. And as you might remember, angles are given in radians. So as you go around the circle, you measure, so you start at 0, pi divided by 2 pi, 3/2 of pi, and 2 pi. And so that's the phase. And we only have one parameter in this very simple model. This IT, which is a current, or you can also think about it as a perturbation to this oscillator. And yeah, it can be time dependent. And just for you to understand what can happen, so you could have, for example, our phase could be increasing in time, okay? And what would this mean? If the phase is increasing in time, it means that actually the phase is going around the circle, right? And in order to see that, we can just wrap the angle in the interval between 0 and 2 pi. So when it reaches 0, then we just reset to 0. So it reached 2 pi, back to 0. And another way of seeing this that is more useful, perhaps, is to use the sine of theta, for example. So if you do the sine of this, then you just get these nice oscillations. So although we are going to focus on this equation for the phase of theta, we are usually going to see the output of this phase oscillator as some transformation. So sine of theta or cosine of theta, which is very similar, as you hopefully remember. So why use the theta model? So the model, it's very simple. It actually describes a stable state, which we are going to say that it's a normal state, and oscillations. It can only do these two very simple things. And when it's oscillating, we can say that the model is representing seizures. Yeah, as you can probably expect, this is really a minimal model. It's as simple as we can get in order to have a model that can give us some oscillations. And so, yeah, if we are going to play with the phenomenological model, then it makes sense to use as simple as possible. And if that's not enough, then we start to construct the complexity on the model and add more components to it if necessary. And of course, since it's so simple, it cannot describe like different normal states or pre-ictal states. This pre-ictal means that states that precede a seizure that we observed in the data. So yeah, this model cannot give you any information about that. Cannot tell you also about seizure evolution, but yeah, that's fine because we are not interested in those questions. So what we are really interested here is to study whether a brain network is more prone to generate seizures or not. And in principle, this model will be sufficient for that, as we are going to see. So yeah, let's play with the model. So to start understanding the model, it is convenient its steady states, as you might remember from Luke's talk. And how do we find the steady states of the Theta model? So we have this equation. So now this is a question for you, if you didn't fall asleep yet. So how do we find the steady states of a model? So this was, Luke gave the answer in the last tutorial. Do you remember?
It's equal to 0, and then we have to find the...
Yeah, that's correct. Thank you. So we solve this equation equal to 0. Why is that? Because if the derivative is equal to 0, then this means that the dynamics is not changing. So this gives us how theta is changing in time. If it's equal to 0, that means that it's just stable. It's doing anything. And how do we solve this? So for simplicity, let's assume that IT is equal to I. We are not really losing anything by assuming that at this point. So we have this equation and we make it equal to 0. And now, so we put this equal to 0, right? Then we just solve this equation. So the cosine We can keep it in this side of the equation. So -1 plus I, that is multiplying here, it's equal to, this one goes to the other side, -1, and this one multiplied by I minus I, it is here. And so we get cosine of theta is equal to this. So this is our solution to this condition. Or if you prefer, you can see theta is equal to the arc cosine of this. So forget about this for now. We are not going to focus on this. It's much easier to just think about cosine of theta is equal to this expression. So let's see what are the consequences of this result. And so, yeah, I will try to go slowly here because this will be the part with a bit more maths. But yeah, if you have any questions, just stop me at any point. So let's try to understand what this means, this solution. So let's remember again the circle. So we have here the cosine of theta. And what we see in the unit circle is that the cosine of theta is bounded between 1 and -1. So it cannot be any value larger or smaller here. So it cannot be larger than 1, cannot be smaller than -1. So that's what I have here. And therefore, we substitute cosine of theta is equal to this expression. This means that this expression should be bounded in this interval. And this expression might be a bit difficult to understand. So what we can do is to just plot it. So let's plot this expression as function of the current I. And we get this kind of plot. It's just this curve here. So notice that we are plotting this between -1 and 1, because that's the interval that we are interested in, right? And so what we find here is actually that we don't have any solutions if I is larger than 0. To this side, there's nothing. There's no solution here. So there might be solutions up there, but we are not interested. They are not useful solutions for us. Yeah, if we decrease more I in this direction, yeah, we still have a solution here, but yeah, it just continues to go and go, and it approaches -1, as you can demonstrate. So depending on I, we find the following. There is one solution at I equal to 0. Why is that? Because let's substitute here I equal to 0. So 1 plus 0 divided by 1 minus 0. So this is equal to 1. So we have cosine of theta. Cosine of theta is equal to 1. And if that's the case, then we are in this point and there is only one solution. So that's theta equal to 0. So that's one special case. Another case is when I0 is smaller than 0. Okay, so we have one of these points here. So when I is smaller than 0, then we have a certain value which is smaller than 1. And if it's smaller than 1, but it's larger than -1, then it means that when we look at the cosine of theta in the unit circle, then we are somewhere in this region. And this means that when we take a certain cosine, actually two solutions. We have one solution up there for this cosine of theta, and we have another down here, right? So they are two different angles, but they correspond to the same cosine of theta, all right? And that's what I wrote here. There are two angles for this in this interval. And yeah, as I said, no solution at I larger than 0. So at I larger than 0, there is no solution here. So cosine of theta is actually larger than 1. Sorry, this expression is larger than 1. Therefore, cosine of theta cannot be equal to that. And therefore, there is no solution. And so what does it mean if there is no solution? Can anyone tell me what does it mean if we have no solution to this equation, take into account that we are studying steady states? Anyone? So I will just tell you then. So if there is no solution, that means that actually if we go back to this means that this condition does not happen. So actually this is always different from zero. It means that the phase is always changing. So there is no steady state. If the current is positive, there is no steady state. That's what it means. So let's look, sorry, let me just ask you, so did everyone understood this part? So if you want to ask any questions, feel free. Okay, let's move on then. So let's look at the dynamics. And if you didn't understand too much of what I just described, don't worry, because what will matter will be like the consequences of these results, not that much the maths in particular. So to look at the dynamics, we can use the Euler's method to simulate the model. And so as you might remember from Luke's talk in the previous tutorial, Euler's method give us this approximation. So we can say that the derivative is equal to this. And what does it mean? So you might remember from his talk when he described the speed of a car, and he was saying that the speed is equal to this derivative. And to have an approximation of this derivative, we can just take a certain interval dt that is different from zero in order to try to get an estimation of the speed. And as we decrease the dt, this approximation gets better and better. And so what does it mean in our case? So we can just rewrite this. So putting this term in this side of the equation, so dt goes to the other side, multiplying there, and this goes to the other side, plus. And this term is our, and therefore we can just simulate this system, okay? So this is actually what you are going to be doing in the practical session. It will be one of the first tasks to do if you then do the practical session. So let's see what happens if we simulate this in our computer. So what happens for these three different cases that I told you about, when the current is smaller than zero, when it's equal to zero, and when it's larger than zero. So it's when we have these different scenarios that I told you. So here I'm showing you for current equal to a negative value, okay? And I'm plotting here 1 minus the cosine of theta. So it could be the sine of theta, could be the cosine of theta. I decided to do 1 minus the cosine of theta. You will understand why later on. It's just convenient. But yeah, you don't have to think too much about it right now. It could be just a sinus, and it will give us basically the same qualitative behavior anyway of the theta. And what matters here is that there is a transient behavior at the beginning of our simulation, and then it reaches a steady state, okay? This is a steady state. It's the phase, it's not changing. And at I equal to 0, we also have some transient state, and then we get to the stable point as well, which, as you might remember, was when theta was equal to 0. So if theta is equal to 0, then cosine of theta is equal to 1, 1 minus 1 is equal to 0. And so we have this here. And what happens at I larger than 0, then so the current is positive, therefore we have no solutions for the steady state equation. That means that theta is always increasing or decreasing, and that means that actually we will have oscillations. So yeah, the phase is going around the circle, it doesn't stop. Yeah. And as you might remember, at I smaller than 0, there were two solutions, and the fact that there are two solutions actually makes the system dependent on the initial condition that we start our simulation. So the initial condition is our theta 0. So at time equal to 0, the point that we decide where to start our simulation. So if we change this initial condition, then we might have this kind of scenario. And basically what happened here is that there was a strong spike at the beginning. So the phase went around the circle and then it went back to the steady state. So this steady state is the same as this one, but the transient things that happen before reaching the steady state were different because of the reasons that I'm going to describe in the next slide. You will also explore this in the practical session. So let's understand better the steady states, their stability. So at I smaller than 0, there are two steady states, as I told you, and actually one of them is stable and the other one is unstable. You might remember these concepts from Luke's talk. And so let's have here again our unit circle. Let's say that for a certain current negative, we have, if we put it in the expression 1 plus I divided by 1 minus I, then we get these two solutions here. So it's these 2 points, and one of them is stable and the other one is unstable. And what it means is that actually the stable one, it means that if we start with an initial condition that it's close to this phase, then the dynamics is attracted to this stable phase there, or from this side as well, gets always attracted. And in the other one, which is unstable, it's the opposite. If we start just nearby this point, then it's the system, the phase is repelled. And so if it starts in this side, then it goes around and until it reaches this point. And if we start in this side, then it goes immediately to this stable point. And that's what we did in the previous slide. So as you may remember, so that's why we have this scenario here and we have this different scenario here. It's because in one case we started below the unstable point in this scenario, and in this one we started above. And by above, I mean that we started somewhere there, and so it was repelled and he had to do the circle to go back to the stable steady state. Of course, if we start the system exactly at these points, then it will stay there forever if there are no perturbations. So even this point, although it's unstable, if you put your system exactly there at the beginning, then it will stay there. But any perturbation will make the system to go away. Sorry, I will be saying very many times system. It's just because it's how we call it usually, but yeah, I'm talking about the phase oscillator. So as I tends to 0, the 2 points actually get closer. Why is that? So if we look at the definition of the steady states, the expression, as you may remember in the plot that I showed you, that as I was going closer to 0, we were getting cosine of theta was getting closer to 1. So this means that, yeah, cosine of theta gets closer to 1, and therefore these 2 points get closer and closer. And at I equal to 0, these 2 points actually merge. There's only 1 point now, okay? There's only one solution. And this is a special case. These 2 points, they were stable and unstable, but now they are together. So what is this? This is a new kind of point, of fixed point in the system, and it's called a saddle point. And it's a saddle point because actually it attracts in one direction. You remember, it was attracting in this direction. So it's kind of keeping the attraction of this point from this direction. But here, from this side, it repels. So yeah, it's a different kind of point because it attracts in this direction and it repels in the other. So it's a kind of the two effects together mixed. At I equal to 0, we have oscillations because this point disappears. There is no stable point anymore. and yeah, all we can have are oscillations. So any questions up to this point? Nothing? Good. So let's continue. What happens at I equal to 0? It's actually called a bifurcation. And it has this special name. You don't have to worry about it, but yeah, it's called the saddle node on an invariant circle bifurcation. It's saddle node because yeah, we have the emergence of this the saddle point that I told you, and it's on an invariant circle because the circle is not changing in our problem. The circle is always fixed. And yeah, what means a bifurcation? It means in the dynamical systems theory that there is a qualitative change in the dynamics of the system. So in the Theta model, for example, oscillations emerge. So for I smaller than 0, there were no oscillations. The phase was always going after some transient period, going to a fixed point, and it would stay there forever. But if the current is larger than 0, then we have oscillations. And yeah, when we have this kind of thing happening, we say that we have a bifurcation, and yeah, the Theta model has this bifurcation. And of course, there are many other types of bifurcations depending on the equations that we could be considering. I just put here some names, but yeah, you don't have to worry about it. And different bifurcations, they would relate with different kinds of changes, with different kind of properties. So for example, if you are interested in this, you can read, for example, Gears's paper, where he talks about different kinds of bifurcations that we could have that could explain the emergence of seizures. And yeah, for example, in this table, he talks about the saddle node, SNCC, which is this one, supercritical Hopf bifurcation, subcritical Hopf bifurcation, and it's showing here that actually they have different properties. So the behavior here, well, you don't have to worry too much about it, but basically it's about how the system behaves when it's close to the bifurcation, but it's not there yet. So let's say in our Theta model, it's when I is close to 0, but it's still negative. And what can happen is that the system can have only a certain stable point, which was the case of the Theta model, but it can also be bistable, for example. That would mean that there would be another fixed point, which is another stable point could be available in the system. So that's another possibility. And when oscillations emerge, so in all of these cases, we have oscillations emerging, and they can emerge with different properties. So, for example, the frequency and amplitude, they can be fixed in the saddle node. In the SNCC, which is our case, actually the frequency of the oscillations, it varies. It starts from 0. And it varies as the square root of the distance to the bifurcation. Anyway, don't worry too much about it. If you want to know more, you can ask me at the end, but yeah, this will not matter too much for us. And actually, you may already have met the Hopf bifurcation that I just mentioned. And this was because you found it in the practical session of Luke's tutorial. So when he asked you to simulate the Wilson-Cohen model, for those that did that, what you found was that you were simulating the firing rate of two populations, excitatory and inhibitory populations in this Wilson-Cohen model, and they were in a certain stable point at this parameter p. And when you change p, actually, when you increase it a little bit, then you see the emergence of oscillations. Anyway, it's just to tell you that, yeah, there are other types of bifurcations besides the one that we are considering here. So let's go back to our phase oscillator. So to summarize what I've been talking about, this Theta model allows us to simulate the following. We have a steady state that when the current is negative, and this is what we can say that represents a normal state, a normal brain activity, okay? And when we have the current positive, then we have oscillations, and these oscillations can represent seizures. So that's just our freedom that we can say that these states define these different activities in the brain. To make the model more useful, we should start making some tweaks to the model. And the first one is to actually add the mechanism of seizure transitions without needing to actually change the current by hand. And one way of doing it is just to say that the current is noisy. So it's to say that our IT, the current, is equal to certain value, I0, certain constant, plus a noise term. Okay, so that's a choice that we can make. And what are the consequences of making the noise current, of making the current noisy? Then in our equation, we replace IT by this, right? That I just showed you. And what we see in the steady state, so if the current, in this case, the current, we are talking about the I0, sorry, here I should have put I0. If the I0 is negative, and we have a certain standard deviation for this noise. So the noise I'm here considering it to be Gaussian noise, okay? It could be any kind of noise that you would like. So we find this kind of activity, some noisy activity, and here's some spikes. Remember that actually what we would expect without the noise, so if the standard deviation of the noise is 0, that's effectively as removing this term, and if I0 is negative, then the activity would just go to certain stable point and stay there. And notice that actually here, now I'm plotting something slightly different from before. It's 1 minus the cosine of theta minus theta s. And theta s here is actually the stable point. This, you don't have to worry too much about what I'm doing here, but what it means is that I'm just shifting the output of the oscillator such that, in such a way that when the oscillator is in the stable point, which is actually given by this, then the output is 0. So it doesn't matter what is the current that we choose. So here should be I0. It doesn't matter what current we choose. As long as it is negative, then we should have a stable point here that should be at 0 when we plot the output like this. And here we are plotting in the same way. And we see that actually because of the noise, we have certain noisy activity, and sometimes we have these strong spikes. And we can say that they are actually interictal spikes. So for those that know about epilepsy, there is interictal spikes. So besides people having seizures, they can also have some short spikes between normal activity, which kind of look like too strong, very strong activity, and yeah, people call them interictal spikes. And so it's nice that in this model we can also have these kind of spikes. And my question for you is, what's the origin of these spikes? So why do we find these spikes in this scenario? Does anyone can tell me?
So somehow it shows, somehow it is a gap between two seizures. That's
could be. In this case, actually, it's we are playing with the fact that we have the unstable point, actually. So if the noise here is sufficiently large, what will happen is that the activity can go over the unstable point. So if you remember when I showed you this picture, oops, it's quite far away, right? So for example, here, so we are in this kind of scenario. We have this stable point and we have unstable point. And so usually without noise, we would just go to this point and stay there. However, if we put noise in the phase oscillator, then it can oscillate here around the stable point, and sometimes it can reach this unstable and it can overcome it. And if that happens, then now it repels, this point repels the phase, and so the phase needs to go around, and so we have a spike. Okay, I hope that's clear. If it's not, let me know. And yeah. So, and what happens if we set I0 closer to 0? So if I0 gets closer to 0, that means that actually the 2 points, the stable and unstable, that they get closer, as I told you before. And if they get closer, that means that actually we don't need too much noise in order to overcome the unstable point. And that means that we are actually going to see more spikes. It's just easier. For the same level of noise, it will be easier to overcome the unstable point and have a spike. So yeah, you will explore this in more detail in the practical session. And consequences on the oscillations. So you might remember that without noise, so when the standard deviation is 0, we could have for this parameter this kind of oscillations when we plot it like this. Well, in this case, you can say that the stable point here, it's 0 because it's not defined actually. And what we find with noise, it's that, well, the oscillations get a bit noisier, so the frequency is a bit changed. We get some noise when it's going down, but overall, this doesn't really matter for our purposes. So yeah, the oscillations change a little bit, but qualitatively, we still keep the oscillations, and that's what matters for our purpose. So what can we do with our oscillator model? We can use it to represent the brain activity of one brain region. That's what we are aiming for. But since we are interested in brain networks, then we need to consider more brain regions and therefore more oscillators. We need multiple oscillators. And what does it mean? It means that, for example, if we consider 2 regions, A and B, then we have 2 differential equations. We need one oscillator for region A and another for region B. So they are basically the same as before, but notice that I put here A for this phase A and this for B. So yeah, 2 regions, 2 phase oscillators, 2 differential equations. And also notice that the currents here, they can be different and should be different. So what we need to actually make these 2 oscillators to interact with each other? So that's a question for you. Any ideas? How can we make the oscillators to interact? What is the condition in these equations? Any ideas? Maybe it's a bit abstract, so I can just let you know. So actually, we can do it with the current. We just need to make the current of one oscillator to depend on the phase of the other. That's the condition for them to interact. So we can say that the current of the oscillator A is equal to a certain function of the phase of oscillator B. So by doing that, and the same, but yeah, with the players changed for B. So by doing that, we are making sure that they interact, because A, the oscillator A will depend on the phase of B. So yeah. And so of course, this is just very abstract. So what's exactly the way that we can make them interact? And a simple way is to just assume that one can excite the other with its output. And that's why the current to an oscillator A can be the I0 as before, the noise, and now we can add this part, 1 minus the cosine of theta B minus theta S. So as you might remember, this was how we defined output of theta b before. And so we are just saying that the current that goes to the oscillator A depends on the output of B. Of course, we could use different functions for this. This is just one simple possibility of doing it. And the same for B. So the same thing, but instead of B here, now we have A, right? And notice, yeah, here just for simplicity, and actually we are going to do it in everywhere. I0 we are just assuming to be the same. The noise, they are independent, but they come from the same distribution. So this means that the standard deviation can be considered to be the same. It doesn't have to be, but yeah, for simplicity, we can make it to be like that. And so we get these two following stochastic differential equations. So this one, so I'm just putting this current I A in the equation for oscillator A. So this was our typical dynamics, and now we are just putting this current there, right? And the same for the other oscillator. Okay, so the equations look a bit long, but I'm just building up. It's still the same things. So let's see the two interacting oscillators. If we simulate this system, what can we see? So here, just one example. When you consider I0 equal to minus 0.1, so it's close to oscillating, but neither of the oscillators are oscillating. So I'm considering I0, it's the same for both oscillators, and the standard deviation is also the same for both oscillators. And yeah, here we have the signal for 1 for oscillator A, and here we have the signal for oscillator B, all right? And we actually see that they are very much correlated. So when one spikes, the other also spikes. Well, not all the time, but yeah, we see a clear correlation between the two. So this is one possible output. Another output, it's to not be correlated. So for example, in this case, it's not so clear that this oscillator A is correlated with oscillator B. Okay, so my question for you is, then what defines whether they are correlated? What do you think? So you may take a look at the parameters. They are actually different. So what do you think defines whether the oscillators are correlated?
Maybe current amplitude over time.
Sorry, can you repeat?
Current amplitude over time.
Yeah, I'm not sure exactly what you mean. Yeah, but the currents, they are different, right? So we are changing it such that here the current is -1, so it means that we are further away from oscillating, and we are putting more noise. So what we are effectively doing here is that the oscillators are more driven by noise in this case, just because, yeah, we increase the level of noise and we make it more difficult for them to spike, just because they are further away from zero, so highs, yeah. But yeah, the most important is the fact that the noise is stronger, and if the noise is stronger, then yeah, they cannot be that much correlated. So let's move on for a network of oscillators, because actually the brain is not just two regions. We are interested in more than two. So if we want to consider n interacting regions, then we need to have n theta oscillators. That means n equations. So for 1, for 2, and for n. So it's always the same thing. You are seeing many equations, but yeah, notice that all of them look the same. The only thing is that, yeah, these currents, they should be different because they account for the interaction with the other nodes. But the expressions, they are equivalent. And so let's Let's consider a case when actually all the oscillators interact with all other oscillators. What does it mean? So we have this equation for a certain I oscillator, okay? So any of the oscillators is given by one equation like this. And the current is given by the following. So we have the I0 again, we have the noise, and now we have a sum over all J oscillators, so index J, summing all the outputs of every oscillator to this node I. Notice that J is different than I, so we are summing over all oscillators, but not by itself, because we consider that the oscillator does not interact with itself. So this is actually a special case when the underlying network is fully connected. So that means that here we have a network. So just for those of you that don't know much about network theory, a network is a set of nodes connected by links. So nodes, these green balls are the nodes, and the links are these edges. And so, yeah, and keep in mind that actually in the literature, people use different names for this. It can be a network or a graph. So network is more used in physics, graph is more used in mathematics, node, which can also be called a vertex, connection link can also be called an edge. And so, yeah, consider this that I just described to you was for the case that all nodes, so in each node we have an oscillator, okay? And each oscillator is connected to all the others. So this is one special case of a network. In general, they don't have to be all connected. And so what happens, for example, if the oscillators are connected at random? So consider, for example, this network. We have, again, 6 nodes. Yeah, for example, node 1 is only connected to 5 and to the oscillator 4. Okay. I will be using oscillator and node interchangeably, but yeah. What it means is that the nodes is the language that you should consider when you are talking about the network. And at each node, you consider that you define an oscillator there. And so now we have to change slightly our definition of the current. All right. So again, it's I0 plus some noise plus now we have these matrix. So these tell us whether nodes are connected or not. This matrix A allow us to define, yeah, whether node J is connected to I. And it's very simple. If they are connected, we can just say that Iji is equal to 1. And if they are not connected, then it's equal to 0. Okay, it's one way of defining this matrix. And this matrix is actually called adjacency matrix of the network. And it's a square matrix, so it means that it's n by n. N was the number of nodes or number of oscillators. And each element in this matrix refers to a possible connection. So it's either 1 if there is a connection or 0 if there isn't. And the diagonal elements of this matrix, they correspond to these AII, they correspond to self-connections. And in this case, we are not considering them because when we do the sum, we do not consider because, yeah, we are just summing over J when it's different than I. So just to give you an example of this kind of adjacency matrix for this network. So it's very simple. So for example, for node 1, we see that it's only connected to node 4 and node 5. So that means that if we go here to the first row that corresponds to the connections of node 1, then it's only connected to in the 4th element. So connection to this one, and here 1 because it's connected to the 5th one as well. And we can see the same for the other nodes. All right, and here, yeah, you see that the diagonal is all zeros because the nodes are not connected to themselves. And another thing that you can notice is that actually this matrix is symmetric. And we are going to see it now because actually there are different types of networks. Just as a side note, you can define an undirected network like this, like before. And in this case, we have this condition. The connection from J to I is equal to I to J, because you say that this node is connected to this node, and this node is also connected to this node. So that's why it's undirected. You have both directions, if you like. So this is actually a special case of a directed network, because in a directed network, you can have it more generally. These can be different from that. So this node can be connected to that node, but this node doesn't have to be connected to this one. It can have only, it has one in connection, but no out connection to this one. You can define it as in and out connections, if you like. Anyway, I'm not going too much detail about this. Oh, I see that I'm already running out of time. So weighted networks, it's another type of networks. In this case, we can define that these elements in the network don't have to be 1 or 0. So for example, if we have a very strong connection, we might define it as being a number larger than 1, all right? So that's just a different kind of network. And actually, whether the brain is better represented by undirected or directory, binary, or weighted network is still an open question. And with the same kind of data, you might be able to infer undirected or directory, binary, or weighted, depending on the method that you use from the same data. Okay, and people still don't know what is the best. But yeah, that's a different question for a different talk. So back to the network of oscillators. So now that we have constructed all of these, we just need one additional thing, which is to add one additional parameter in this equation. So now I put here k divided by n. And why I'm doing that is just to weight this whole term of interaction. So as I told you, this kind of gives you a property about the single node. So if this is negative, then the node should be in the steady state if there is no noise and no interaction. And this is the noise, gives you this variability in the dynamics of the node. And then there is the contribution from all the other nodes in the network. And I see that I forgot to close here the parentheses. Anyway, and k divided by n is just useful in order to just change how much value you want to give to the interaction as compared to the single node dynamics. Okay, it's just a convenient way. And we divide here by n, the number of nodes. It's again just for convenience, because if the network is larger, then it means that you would be summing more or potentially more elements here, and that would change your results. And therefore, it's nice to divide by n, because then k is usually like more stable in a way. Anyway, those are details that you are actually going to study in the practical session. So what kind of dynamics can we observe in a random network? And so remember this random network, if we put our model in this network, then we can find for these parameters, notice that we only have basically 3 parameters, because we are considering all the nodes kind of equivalent apart from their connections. And yeah, for these parameters, we find this kind of dynamics. It looks like, for example, obvious thing that you see here is that node 2 and node 3, they are not oscillating as much as the other nodes. So these nodes seem to be having more spikes than node 2 and node 3. And that's kind of obvious because of the connectivity. So node 2, in this case, only has one connection, and node 3 also has only one connection. Whereas all the other nodes actually have 2 connections, and that means that they receive more inputs, and therefore they are more likely to oscillate. But yeah, this is very simple in this case because it's a very small network with very simple properties. It's not always that simple. And you will explore these with some small differences in the practical session. So what is this useful for? It's useful because it allows us to test a number of hypotheses. So at the beginning, I told you that we can actually use mathematical model to evaluate the structure of brain networks to define and check the propensity of a certain brain network to generate seizures. And so that can be useful for the diagnosis of epilepsy. So imagine that you get, you infer brain networks from healthy people and also from people with epilepsy. Now you can find differences in the networks, but only using the model, then you can really test the hypothesis that the networks coming from people with epilepsy, they should be more likely to generate seizures in the model as compared to the networks from people, from healthy people. So that's one possible applicability for the diagnosis of epilepsy. We can use this framework. Another is to the diagnosis of epilepsy type. As I mentioned at the beginning, actually seizures can be generalized or focal, depending on if they engage the whole brain or not. And actually, if we have a brain network, we can test in our model whether the seizures seem to propagate to the whole network or not. And so again, this framework allows us to test from a brain network whether we predict that it should be the network from someone with generalized epilepsy or focal epilepsy. And it can also, it allows us also to study epilepsy treatments such as brain surgery. In brain surgery, what people do is that, so if medication does not work to stop seizures, then they might try to find what is the brain region that is responsible for seizures, and they remove it to see if it stops. And this framework gives us a way of testing different hypotheses. We can study different perturbations to the brain network, removing different nodes and seeing whether it stops seizures in the model. And yeah, all of these, me and the other people, we have published different papers. So if you want to take a look at that later, you are more than welcome. And as I said at the beginning, this is not only useful for epilepsy. So actually, it has been used, for example, recently in this paper from Deco's group, published in Neuroimaging, to study the transition from wakefulness to sleep states. So I'm not going to details because, as I said, I already run out of time. But yeah, you can check the paper, and you can also study the relation between functional networks and structural networks. You can study, yeah, how robust is the neural dynamics to changes in white matter. So these models, I mean, it doesn't have to be this Theta model. Of course, you can change the Theta model and use a different model depending on your hypothesis. And then, yeah, then you can just use the same kind of framework. And yeah, it can allow you to study other neurological diseases and treatments. And with this, I conclude. If there are any questions, they are more than welcome now. Otherwise, we are going to move to the practical session. Any questions?
Sorry, do you think this model can be also used for source localization in order to reduce the number of electrodes? If you want to implant electrode, for example, if this network or this sub-network in the brain are correlated, we don't need, for example, to implant too many electrodes in just one region of the brain if they are correlated.
Yeah,
because that's another difficulty for source localization.
Yeah, that's an interesting possibility. Yeah, I think, yeah. So very related to that, I actually did something very similar in one of those papers that I put in the literature here. In this paper, which one was it? Oh, it's not here. No, it's here. This one in clinical neurophysiology, it is here. Actually, in this case, what we did was to study functional networks from scalp EEG, and we studied these functional networks in the source space, and then we put our model in order to predict what were the regions that would be more responsible for seizures, and that could guide where to implant the electrodes for people that need intracranial implantation. Yeah, for people that then receive surgery for epilepsy. Yeah, I'm not sure if this answers your question, but yes, you can study it with functional networks in the source space, for example.
Yes,
Marinho, could I just add to that response? Yeah. So also something that you'll learn about at the next session with Alex is something called dynamic causal modeling. So what this does is it takes this framework and it tries to model the source space and then maps through to the electrodes. It uses a lead field to map through to it. And so in theory, the idea of this dynamic causal modeling, which is fitting this framework to the data, should get rid of the need to source reconstruct. Now, I'm not saying whether I think it does completely or not, but in theory, that's the idea. So that's one way that this framework can also be used.
Oh, okay.
So you'll learn about that at the next session.
Awesome, thank you.
Yeah. Any other questions? If not, then we are going to move to the practical session. So how does it going to work? So actually, the practical session is divided in 3 parts. So in the first part, you are going to simulate a deterministic phase oscillator. So I will give you about 15 minutes to think about the problem, and then I will try to give the solution like in 5 minutes and also to answer some questions. Then the next part will be simulate a stochastic phase oscillator. Again, I might give you about 10 minutes or 15 minutes for that. And the last part is to simulate a network of interacting phase oscillators. As you probably read in Luke's email, you can download all the worksheet and also the code from GitHub, from this link. And in this folder, you can open the subfolder practical 2 and open the document worksheet 2. And yeah, when you open MATLAB, don't forget to change the directory. So this was made thinking that you would use MATLAB to solve these problems. Of course, you could use other languages. And there is also a folder with solutions. Of course, you should first try to solve it by yourself. And if you have any questions, then you can just ask the tutors, which will be me and Luke and also Dominic and Alex. Yeah, so we will divide you in breakout rooms. So whoever wants to stay to do this, then yeah, Luke will separate people in breakout rooms, and then yeah, the solutions will be discussed in the main room. That means that everyone will be brought together to the main room once we go over the solutions. But in the breakout rooms, you feel free to discuss with each other the problems. And for those of you that might consider instead doing this later on by yourself, then yeah, you can ask questions in this forum that we have set up. And yeah, that's it.